We know that the universe is expanding, and it's expanding at an accelerated rate. And for that, there is a rate at which it expands. The big question is, what is the rate of expansion of the universe? Very well. Astronomers try to calculate this expansion rate in two main ways. One of them is by looking at the cosmic microwave background radiation. In other words, looking at the primordial universe. That's one way you can calculate it. The other way is by looking at closer objects. And for that, we use standard candles, which we call Cepheid stars, and supernovae. What's the problem? The problem is that when we use the cosmic microwave background radiation, the result we get is 67 kilometers per second per megaparsec. And when we use Cepheids and supernovae, the result we get is 73 kilometers per second per megaparsec. It's a significant difference. It shouldn't be this way, and this has created what we commonly call a cosmological crisis. We don't know what the expansion rate of the universe is. Maybe it expands at one speed initially, then another, but we don't know. Astronomers are trying in various ways to answer this question. Very well. One idea is as follows. If we can see some type of very distant standard candle through gravitational lensing, we will see that standard candle, for example, a supernova explosion, not just once, but we would see it repeatedly, because that's one of the effects of gravitational lensing. And these repeated views indicate what? That each repeated image we are seeing took more or less time to reach us, because gravitational lensing occurs due to a cluster of galaxies, and light takes different paths. So we have a time interval between the repeated images that we see, and researchers, people in cosmology, have managed to determine a way to calculate the rate of expansion of the universe through this time delay. They say it might be the most accurate way to do it. What's the big problem? The big problem is that if it's already difficult to observe a supernova, imagine observing a supernova way back in the early universe through gravitational lensing. It's even more complicated, isn't it? Yes, it is. But who comes into play here? The James Webb Space Telescope, which has one of its main features we've seen in the past year of its scientific data. One of the main features is to observe gravitational lenses in great detail and discover very distant galaxies, discover Einstein rings, Einstein crosses, which are all styles of gravitational lenses. So the James Webb is becoming an expert. It's becoming specialized in this type of detection. Very well. And that's exactly what the James Webb managed to do. It observed a very, very large galaxy, call it a massive cluster, called G165. In this cluster, it discovered several gravitational lenses. You'll see the images. They're sensational. The gravitational lens images from the James Webb are truly out of this world. But the most interesting thing in these images is not the gravitational lenses, the distorted galaxies it discovered, but rather it managed to detect a supernova there. And it's not just any supernova, it's a type 1a supernova. Why is the supernova important? Because this is precisely the type of supernova that astronomers like as a standard candle. And then you might ask, why do we use Cepheid variables or supernovae for this? Well, one of the great difficulties you have in the universe is calculating distance. And distance is the key factor when you're going to calculate the Hubble Constant, which is nothing more than measuring the rate of expansion of the universe. To calculate the distance of a distant object in the universe, you need something with a very distinctive brightness, because then, through brightness, through luminosity, you can arrive at the distance with greater precision. So Cepheid variables serve this purpose very well because they are variable stars, but when they flicker, you can calculate their brightness very accurately. And type 1a supernovae as well, because when a supernova occurs, when a supernova explosion happens, they shine brighter than an entire galaxy. In other words, you have a very good marker there. You have what we call a standard candle. And in the case of a supernova that has undergone a gravitational lensing effect, that's even more interesting. So this supernova, discovered by the James Webb, is the second most distant supernova ever discovered. It exploded 10 billion years ago. That's really cool. And it doesn't appear just once, remember what I said. It appears 3 times because the image is passing through a gravitational lens. So this image is repeated. So it means that astronomers will now be able to calculate the time interval between these images. And if they can calculate it, it's not a galaxy because a galaxy has a somewhat diffuse brightness, but it's a supernova that has a very distinctive brightness. In other words, it's easy to calculate these things with supernovae. They will calculate this time interval, and from this time interval, they will be able to use it to calculate the Hubble Constant and thus estimate the rate of expansion of the universe. What does this mean? This means that a supernova that exploded 10 billion years ago may, along with the James Webb, because it was the one that discovered it, finally save cosmology and resolve the cosmological crisis we're living through. That's really cool. This supernova was named H0PE, but when you read it in a more interesting way, it's being called the supernova hope. In other words, it's our hope to be able to resolve the major cosmological crisis. Now you might ask, where's the calculation done by the astronomers? Very well, they haven't done the calculations yet. They mention in the articles, in the releases that have been published, and in the actual paper that they haven't done this calculation yet. They are characterizing this supernova in the best possible way, so that they can then do the calculation, and with the calculation done, see if they can solve the cosmological crisis. Will it come closer to one of the measurements? Will it come closer to the other one? Will it yield a third measurement? And how will it be? Remember, it's not just this way, okay? Astronomers are also using neutron star collisions to resolve the cosmological crisis. The only problem with all of this is the following. A supernova through gravitational lensing is very difficult to detect, very difficult, and a neutron star collision is even more difficult. What does this mean? It means that perhaps the 2 ways we have to solve the cosmological crisis are ways to use astronomical objects or phenomena that are very difficult to detect. But astronomers have the foundation, the hope that they can do it. And now, with the James Webb, they can also explore other clusters with different gravitational lensing effects and try to search for other supernovae like these, which have a repetition, and from the repetition, calculate the time delay, the time interval between them, and then apply it to calculate the rate of expansion of the universe. If they can do this for more supernovae, then they can have a good statistic and find out if this works or not. So there's the James Webb helping out, and a very ancient supernova from the early universe, perhaps helping astronomers resolve the cosmological crisis, one of the biggest existential crises in the world of astronomy. All right, folks, this was the video I wanted to bring to the channel for you now. I hope you enjoyed it. If you did, you know the drill. Never forget the YouTuber package, share, favorite, subscribe to the channel. If you're not already subscribed, leave in the comments what you want to know. And don't forget to watch this other special video I made for you.